Today, we are going to discuss Faraday's electromagnetic lab. And for this, just come to the link given you in announcement. This link will reach to you this page. And to get the report template, just click over here. It's about magnetic field and electromagnetic induction. And from here, you are going to download the simulation. It's the Java program. And so once you download it, you just open it by clicking on it. It's actually 5 different simulations in one. And this multi-featured simulation intend to lead you to understand many parameters that affect magnetic flux and how changing flux can induce electric currents. In the first step, called bar magnet, we begin simply by showing the static magnetic field around a permanent bar magnet. These miniature compass needles are used to visualize the field. Notice that the compass needles fade as a magnetic field gets weaker farther from the magnet. As you know, the reason for this weakening is that the magnetic field strength gets weaker as it gets farther from the magnet. This movable compass needle shows the direction of the field. If we move the compass around the bar magnet, we see that the direction of the field is changing, and as you know, the direction of magnetic field is defined to be the direction in which the north pole of a compass needle points. And we have a more sophisticated field meter which shows the magnitude and components of the field in units of Gauss at the location of the crosshairs. If we move the field meter around the magnet, we can see the value of the magnetic field of the point where you place it. There is also a slider in the menu that you can change the strength of the magnet. In this part, I expect you to find the magnitude of the largest possible field in this simulation and explain where you found that maximum field. Once you find this point, please add this screenshot to your report from here. You You can switch from one simulation to the other by using the tabs at the top of the simulation window. In the Pickup Coil tab, we have a coil wire attached to a light bulb. Notice I can change the number of the loops in the coil. Or I can change the area of the coil. When I move the magnet, have a changing flux in the coil, which induces a current which lights the light bulb. It's only the relative motion of the magnet and the coil of matter, so I can move either the coil or magnet and get the same response. What happens if I flip the polarity of the magnet? When I flip the polarity of the magnet, reversing it 180 degrees, I get a large change in flux, which lights the bulb. Okay? In this simulation, as I showed you, there are at least 5 ways to get light bulb to light up briefly. In this part, I suppose you to list the methods you come up with to light the bulb. Notice the blue squares in the wire, which represents the electrons. When I change the flux, the electrons move in the direction predicted by Lenz's law. As the magnet moves to the right toward the coil, the external magnetic flux through the coil increases with time. To counteract this increase in flux due to a field toward to the right, the induced current produces its own magnetic field to the left. Hence, the induced current is in this direction, which opposite to the direction of the movement of the electrons. Let's see again. The movement of the electrons is like that, and the direction of the current is like that. There are also questions you have to answer here. I just leave it to you to find the answers will be, and the electromagnet part let's flip to the electromagnet tab. We have a coil attached to a battery. The battery drives a constant current that makes the static magnetic field. Notice that the field created by this coil of current is just like the field created by this permanent bar magnet. In fact, in the bar magnets, The field comes from the microscopic currents due to the spins of electrons. Now, I can change the voltage on the battery and thereby change the current and the magnetic field. If I flip the polarity of the battery, that's just like flipping the polarity of the permanent bar magnet. If I oscillate the voltage on the battery, I set up an oscillating current in the coil. And this is just like driving the coil with AC current supply. This is a graph of amplitude and frequency of the driving current. The vertical axis of the graph is amplitude and the horizontal axis of the graph is frequency of the driving current. As you see, the magnetic field's both direction and magnitude changes with coil connected to the AC source. In the transformer tab, we see a particularly important application of all these ideas. We have two coils. One of them is driven by a constant current and the other coil is hooked to a detector, either a light bulb or voltage meter. We call this detector coil of pickup coil. And as in the other tabs, I can change the number of the loops or I can change the area of the loops. I can change the voltage of the electromagnet. And also I can flip the polarity of the electromagnet. I can move either magnet or pickup coil. As you see, I can explore many parameters that allow me to change the flux and thereby produce a signal in the pickup coil. I again want you to list the methods you come up with to light the light bulb in this part. As I showed, I can either light the light bulb by keeping the current fixed and moving the coils, or I can keep the coils fixed and change the current, the driving current, with this AC current supply. The AC current supply allows me to change the both frequency and the amplitude of the driving current. Notice that by changing the number of the loops in the pickup coil, of keeping everything else fixed, I change the amplitude of the voltage in the pickup coil. This device is called a transformer because I'm transforming the voltage from the AC current supply into a different voltage in the pickup coil. This simple device, the transformer, is used all over the world and electrical generation and distribution. It's an essential part of the power grid. There are questions you have to answer in this part. I again leave it to you to answer these questions. In the final tab, we show the essentials of an electrical generator. Here we have fast, which produces a waterfall, which spins the permanent magnet. The spinning magnet produces an oscillating flux of pickup coil. Which drives a current which lights the bulb. Almost all power plant generators work on this principle of an oscillating magnetic flux, which is why we have a AC current in our homes. How get the brightest light? Of course, the answer is the largest waterfall, the strongest magnet, and the most number of loops, and in the pickup coil give us the brightness light. Unlike what you have observed previously, increasing the area of the pickup coil in this situation produces more voltage. I expect you to explain why more area corresponds to a larger voltage in this simulation. This will finish up your experiment, and unlike the other experiments, you have 1 week to prepare your reports for this experiment. If you have questions about the experiment, you can ask me by mail.